Hello, thanks for stopping by and welcome to Narrowboat Maths class. We're getting loads of questions, well, a couple, on the mathematics and the calculations that we've used in the narrowboat design. Such things as how much ballast are you using, what's the ventilation, what does the boat safety scheme say on certain things. So we thought we'd do a little short video on maths. Oh, I do hope this isn't mansplaining. Math. So a question we're getting from subscribers is, how much ballast do we need to ensure the prop and rudder are below the water level?
Say again, Houston, ballast?
So Archimedes' principle is that a floating object will displace the same amount of water as its own weight, and that's critical to calculating ballast. Now we know how much of the boat is designed to be below the waterline, the draft. Therefore, we know the amount of water to be displaced is the total weight of the shell plus the weight of the engine, the mechanicals, the fit out, and the ballast. Let me demonstrate. Okay, it's a really crude demo. Bucket of water representing the canal, plastic tub representing boat. You see how it just sits on it? We need to get the boat underneath the water so that the water is over the prop and the rudder. So how do we do that? Well, let me get some ballast. And that's what we're trying to calculate. So if we put in some ballast, you'll see that the boat now sinks in. And it's perfect because we've displaced the appropriate amount of water. But if we get the ballast wrong, what happens? We have to, it could sink. And we don't want that. So, what we need to do is, put some more here, calculate it out. And you'll notice that as I put ballast in, it's moving. So if I put too much on one side, we get the same issue. It'll keel over and it will sink. So we have to work out not only the amount of ballast, but the weight of the engine, the weight of all the wood that we're going to put in the boat, the weight of the cooker, the calorifier, the water tank, and then we have to make sure that there is enough ballast distribution to make that correct. So it's an estimation. We will make an estimate and then we'll add and remove ballast once we start trimming up the boat in the water. Hope that makes sense. We know all the dimensions of the boat, so we can calculate the displaced volume. We know the weight of the shell and we can estimate the fit out weight. From this we can get a first approximation of the ballast required. So we now know the displaced volume, but the boat isn't rectangular. So we need to take into account the swims and the other design elements like the bow. So let's reduce that volume by, say, 15%. So there you go. I hope you found that useful and not too mansplaining. But that's how we got to 4 tons of ballast that we needed for the boat. So we're going to go off and get that ballast now. Material-wise, engineering bricks can be used. Concrete common blocks of concrete bricks can be used. They're a bit lighter than the engineering bricks, so you need more of them. Or you can use steel, or you can use paving slabs. There's a whole variety of different ways. But for us at a price point, concrete common block is the one that we're going for. So another important calculation is how much ventilation do you need? And that will comply with the RCR and the boat safety scheme. And it's high and low ventilation, and it's a little complicated, so bear with me while I go through this.
Terrible ventilation.
The essence of the regulation is to make sure that there is sufficient airflow, sufficient oxygen, to make sure there's no build-up of carbon monoxide gas, which we know is absolutely deadly and can't be detected by smell. When you come to get your boat safety scheme certificate, the examiner will look at all of these things, how your ventilation works, and be pretty stringent about it.
Stringent, tough, inflexible.
So there's a set formula for calculating the ventilation, but to use the formula you need a bunch of other information. You need to know what your output of your gas cooker, your oven is. You need to know how many people are going to be on the board, typically for staying overnight. You need to know the outputs of things like your diesel stove or your solid fuel stove, etc. And I strongly recommend looking at the boat safety scheme leaflets. Their stay safe advice for carbon monoxide is an invaluable document for calculating ventilation. This table shows the free air volume from various vents in a narrowboat that the BSS will use. We will use these later in our calculations.
That was math.
So I hope that wasn't too boring. But why is it so important? Well, for us at the shell design stage, we need to ensure the correct vents are designed. Later, if we change, say, the stove or the fire or the cooker, etc., we need to ensure that the calculations are still correct to meet the regulations. At this stage, we don't want to be discovering we need to cut more vent holes in the boat. In this section, we'll look at cable sizing and fuse sizing. Now, there isn't a one size fits all on a boat. You really do have to calculate it out. Now, I'm no electrician, but from the research that I've done, this is what we've come up with.
All decks, red alert, prepare to leave orbit.
Now, I'm not going into all of the details for AC and DC electricity. There's loads on the internet for that. For our purposes on the boat, we need to know that voltage decreases over distance, and thus we need to make sure the cables are big enough to limit the amount of voltage drop and the end appliances has the right power to operate.
Simple matter of voltage.
Now, it's really important you understand what your power needs will be, so you really need to do a power audit. Using what we know, we can calculate the amps. Once we've estimated the usage, the total amps needed, etc., we can total it all up to give us our battery size, 200 amp hours, 300 amp hours. Or we can remove things when we realise we have too much stuff and we need a nuclear power plant on board. And now we need to work out the last part of the equation, which is the distance the cables need to travel. So we're now getting close to understanding cable sizes. We know our appliances and their power needs, and we know where those appliances are located from, obviously, our design plans that we've done. So we now look at compensating for the voltage drop over distance. So now we can make use of one of the many voltage drop calculators available. You enter in your voltage, your current that you need, and your distance of your cable, and it will work it out for you. It presents you with a list of cable sizes and the voltage drop, and we're looking for that 3% magic number. So you end up with a big spreadsheet with all your appliances and your max power usage. So you can effectively size your batteries and know what cable and fuse sizes you need. Now this is not a detailed insight, but we're trying to share the mathematics and the logic behind the cable sizing. I kind of hope you found it interesting. It's not hard, but it is really time consuming. Boy, is it time consuming. And sometimes it's quite hard to determine the power usage of an appliance, and you just have to do your research and your manufacturer data. You're never going to be absolutely perfect with this, but knowing the distances of your appliances will give you your cable sizes, manage your voltage drop, hold it to 3%, and it should be good enough. It's not an exact science. It is a boat.
Holy voltage!
The other main electrical calculation we need to do is around solar. How much solar power do I need to charge my batteries?
Solar power, it's the future.
Now, I'm not going to go into all the details of battery types, deep cycles, discharge rates, etc. But our battery bank makes allowances to give us 2 days of battery power without recharge or running the engine. Similarly, we're not going to go into the detail of the different solar panel types and how to wire them. Suffice to say that we're going for monocrystalline panels because it's better in the shade, good for the canals, and we're going to wire the panels in parallel because we want to eke out enough amps to charge the batteries. So the next thing we've done is we've worked out the solar panels that we want for the available roof space. So we've gone for 4 125 watt panels. Those give 29.5 volts each, delivering 4.07 amps each. And we can use all of that in our calculations. So we can take the details from our solar panel and we can work out the sizes. So 4 times 125 watts is 500 watts. 4 times 4.07 amps is 16.28 amps. And they're wired in parallel, so the volts will stay the same at 29.5 volts. So we can use that to verify. So using Watt's law, which is P equals IV, Watts will then become 16.28 amps times 29.5 volts, which is 480.26 watts. So more or less exactly the number that we're looking for. So using Watt's law again, we can determine the size of the solar controller, the solar regulator that we need. So we've got 500 watts of solar divided by 12 volts gives us maximum of 41.66 amps that controller needs to handle. Now we go buy one.
The solar arrays have been optimized.
So that's fine, we know the size of the solar controller that we need, but just how long will it take to charge my batteries? So now the math is pretty simple. We have 600 amp hours of battery at 12 volts, which is 7,200 watts of power. So that's 7,200 divided by 350 watts of solar power is 20 hours. So in theory, it would take 20 hours of sunshine to charge our batteries from empty to full. No way in the UK is that going to happen.
My head hurts.
So there you go, another lesson done, and I hope you found it useful. It was fun trying to figure it all out. Now, solar in the UK, particularly the shaded canals, is a challenge. But if we can put a good amount of solar into our batteries, we'll run the engine or the generator less, and that's fine. In the UK, we get 2 to 3 days of sunshine in the whole of the summer. It'll be fine.
Thank goodness that's over.